So, let me summarize Simpson's one-third rule. One-third rule. It states that let f be an integral function or integrable function rather. It is an integrable function in the interval a and b, that is its integrable in the whole range a b. Now, if f is interpolated by a quadratic polynomial, P2x between the points a, b, and of course, a plus b by 2, that is the midpoint between a and b. Then the integral of f fx. So, let us write fx and this is also fx. The integral of fx is approximated by the integral of P2x. So, which is a to b f of x, it is equal to a to b P2 of x, and which we have seen that has a form which is equal to f of a plus f of a plus b by 2 plus f of b. Okay. Now, one thing is worth noting here is that we have used Newton's interpolation formula, okay, for arriving at this expression of Pnx or the P2x. We can as well use the Lagrange's interpolation or any other interpolation, and even Taylor series expansion of a function about certain point is also going to give us the same formula. We will try to address some of these issues in the tutorials, but however, let us at this moment keep it the derivation be kept only with the Newton's interpolation polynomial as we have done. Okay. But as I said that the Lagrange's interpolation or any other interpolation scheme would have given the same result as it is written here. So, the I is equal to this. So, this is known as Simpson's one-third rule. So, let us see some more examples of this and how to use this. So, example, so the distance covered by a rocket. So, it is a physics problem or a aeronautical engineering problem if you like, by a rocket in meters from t equal to 8 seconds to t equal to 30 seconds is given by x, which is equal to 0 to 30, okay, and it is the integral of, sorry, not 0 to 30, it is between 8 and 30. So, it is 8 to 30, and so this is 2000 log of 140,000 divided by 140,000 minus 2100 t minus gt, which is the g has a value. So, let us write the value itself, it is 9.8 t and then a dt. So, this is the formula for the rocket motion. Of course, this formula or this kind of motion you have not seen much, but it goes as a log, and then of course, the time appears in the denominator of the argument of the log, and then of course, there is also a gt term. In any case, say this is given, and now one has to compute it or evaluate the integral using the Simpson's 1/3 rule. So, the questions are as follows: A, use Simpson's 1/3 rule to find the approximate value of x. Okay. Second is of course find the error, or whatever you call it, relative error or percentage error, find the error in this. So, we will use a simple Simpson's 1/3 rule, that is not use any segments in between. So, the formula is simply x is equal to b minus a by 6, f at a, just what it was written there. Excuse me, I forgot a factor of 4 here. Okay. This is very important, this factor of 4 is very important. So, this is not just f a plus b, but it is 4 in times f a plus b. All right. So, this is a 4 f a plus b by 2 plus a f b, and so this is the formula. We have b equal to, so let us write a equal to 8 seconds, b equal to 30 seconds. I am only writing it in terms of just numbers. A by a plus b by 2 is 30 plus 8 is 38, and this is, so this is 19. So, all in seconds, so f of t, that is the integrand which you otherwise would have used a polynomial, but that the integrand is given here is simply 2000 log of 140,000 divided by 140,000 minus 2100 t minus 9.8 t. So, we have to find 3 of them, f at 8, f at 30 and f at 19. So, let us calculate all those things. So, f at 8, it is 2000 log and 140,000 divided by 140,000 minus 8 into 2100 is 008 and then 168 and so on, and this is 9.8 into 9.8. Okay. And then if you simplify this, this becomes equal to 177.27, and if I am allowed to use a unit, because it is you have to multiply it by dt, that is which has a unit of time. So, this second will cancel and I will get a meter. So, the integrand has the dimension of meter per second, which is velocity, and which is known that x is vt and dt. Now, let us calculate the other two. So, this is 1. So, f of 30, that is at the end point, it is 2000 log of again 140,000 divided by 140,000 minus 2130 and minus 9.8 into 30, and this one has a if you So, it is 901.67 meter per second. So, the rocket travels in this interval from f8. The integrand is actually the velocity, rather the velocity increases from this value, which is 177 meters per second to 901.67 meters per second. But what is important for us to get the other one, which is f of 19, you can write down for these time as 19. Finally, what you get is that it is a 484.75 meter per second. Okay. So, now I got the value of the function at all the 3 points, sampling points, which are the end points and plus a point at the middle. So, now I am ready to put it there into the formula, which is b minus a by 6, which is 30 minus 8 divided by 6, and we have f of 8 and a plus a 4, f of 19 and plus f of 30. Okay. So, that is this, and if you simplify this, this becomes equal to 11065.72 meter. Okay. Now, the exact value, so this is part 1. So, this is the distance travelled, you get it. And for part B, for calculating the error, we need to know the exact value. So, the exact value of the integral, this I am not showing it, but you can do it easily. Value of the integral, it is equal to 11061.34. Okay. So, you simply have to integrate this expression, which is a log of this. So, it is like a log of a by b, which you can expand as log a minus log b. So, the log a term will give a constant, which when you integrate it over dt will give you just a t, and the log x, so to say, log x dx can be integrated, and between the limits t equal to 8 to t equal to 30, and finally, what you get is this value, the exact value of the integral. You see, you have gotten pretty close in terms of the number, excepting that it varies only at the 5th decimal place, not the 5th decimal place, 5th place, that is in the the ones place, as it says. So, this is the value of the integral. So, in case you want to know the error, so the error, the magnitude of the error, or rather the error itself is like 11061.34 minus 11065.72. So, this is like a minus 4.38 meters. So, this is very small, right. I mean 4.4 meters in some 11,000 meters is very small. So, the relative error is basically, so the percentage relative error is, so it is 4.38, and I will take the absolute value. So, take the absolute. So, it is 4.38, I will not take the sign here, and 11,061.34 into 100 and in percent, and it gets only 0.0396%. So, just one interval, or rather the bare Simpson's 1/3 rule for this problem of rocket motion is gives you a value which is pretty close, and it is only off by this 0.04%, say for example. Okay. Now, let us compare it with a multi-segment or multiple segment Simpson's 1/3 rule, which we have learned, that if each of the if you divide the entire interval into n such segments and then apply the rule, the bare rule, Simpson's 1/3 rule for each one of those segments and then add all the contributions up, and this is certainly going to be a better approximation for the integral. So, we will solve the same problem, okay, using multiple segment. So, here of course, we have to divide the interval into the entire interval by n, and we have seen this formula earlier, and if you want the, I will again write down the value of the integral. So, it is h over 3, that is a value at a, and then there are 4 times the value for the odd numbers. So, it is f of x 1 plus f of x 3 plus f of x n minus 1. So, these are all the odd numbered intervals, or rather the sampling points, the values of the function at all these odd sampling points, and twice for the values at those even number of sampling points. It is f x 4 and so on all the way up to f x n minus 2, and finally, the f of x which is x n, which is equal to b. So, let us just make that distinction. So, x 0 and x n. So, just to make sure that we know that f of x f of a equal to f of x 0, that is the value of the function at the initial or the left extremity of the interval, and this is at the right extremity of the interval, is they are called as x 0 and x n, and the values are values of the function are like this. So, the important part is that for this multiple segments Simpson's 1/3 rule, what you have to do is that you have to take all the sampling points, odd number of sampling points such as 1, 3, 5 and so on, and multiply it weighted by 4. The even numbers will have to be weighted by 2, and the leftmost point and the rightmost points are left alone with a weight 1. Okay. So, if this is there, so this is what we had written earlier in a slightly compact notation. So, it is b minus a by 3 n, and we have a f of x 0. So, let us this plus 4, and this is like I equal to 1 to n minus 1, make sure I is odd, and then I have a f of x I, just the second term. Then I have I from 2 to n minus 2, and I have f of x I with I being even plus f of x n. Okay. So, this is that, and then we want to solve the same problem use. So, the question is use 4 segment Simpson's 1/3 rule to find x, find the distance travelled by the rocket. And find of course the error that goes with it, and you will see that the error is negligibly small. Okay. So, let us try calculating all these things. So, what is this n is now 4. So, we have a solution that needs to be done, n equal to 4, 4, a equal to 8, b equal to 30, h which is the step size is equal to b minus a divided by n, which is 22 by 4, which is a 5.5. So, and of course, f of t, for reminding ourselves, it is a log of 140,000 and 140,000 minus 2100 t minus 9.8 t. Okay. So, f at t 0, we are calling it x 0 or t 0, which is f of 8, which we have already calculated earlier. We can take that value, which is 177.27. Now, f of t 1 is simply f of t 0 plus h, which is equal to f of t 0 is 8 plus h is 5.5, which is equal to 13.5. So, if you calculate f at 13.5, this comes out to be equal to 320.25 meters per second. So, you are taking more terms in the interval. And what is f 2? F 2 is farther, f of t 1 plus h, which is f of 13.5 plus 5.5, which is nothing but f of 19, and we know f of 19. F of 19 is nothing but we have calculated it earlier, 0.75 meter per second. And similarly, the f of t 3, which is nothing but equal to f of t 2 plus h, which is equal to f of 19 plus 5.5, which is equal to f of 24.5, which is nothing but equal to which if you calculate it, it becomes 676.05 meter per second. So, that is f t 3, and then of course, the final one is known, f of t 4, it is equal to f of t n, so to say, which is 30, equal to f of 30, and whose value also we know because we have calculated it earlier, 0.67 meter per second. So, this is there's that. Okay. So, so we have all these things. We have one here, one here, one here, one here, one here. See that these two will have to be left alone because in our formula they appear with weights 1, that is the first one and the last one. Now, the odd ones will appear with weight 4. So, there is one odd and one odd here. So, they will appear with weight 4, that is this has to be multiplied by 4. Let me show you. So, this has to be multiplied by 4 and this has to be multiplied by 4. This will have to be multiplied because it is a second one which is an even, it has to be multiplied by 2, and of course, as I said, the first and the last will have to be left alone in order to so fit into the formula. Okay. So, if we put in everything, so my x will become 30 minus 8 divided by 3 into 4. So, that is 22 by 12, and then I have f of 8 plus 4 times f of t 1 plus 4 or let me write it in a bracket, so that things become more they look same as the way we have written, 2 f of 2 t 2 and then finally f of 30. So, if you put all of them and then simplify this, this comes out to be 11061.64 meter. The exact value we have already said, but let me write it here. The exact value is 11061.34 meter. So, this is really close. So, the error is 11061.34 minus 11061.64. So, it is actually in the second decimal place or rather the first decimal place it is differing, and then this becomes as a 0.30 meter. Remember, this was about 4 meters, whereas this is less than a meter, less than even half a meter, it is 0.3 meters. So, the absolute percent relative error is this 0.3 divided by 11061.34 and multiplied by 100 in percent, and this becomes as 0.002727%. Okay. That is a really small error, and you can pretty much approximate it to be the exact just by using n equal to 4. So, if you continue it to n equal to 6 and n equal to 8 and so on, you will see that the error is reducing and it becomes vanishingly small for say n equal to maybe 8 or maybe n equal to 10. Okay. So, this tells you that this Simpson's 1/3 rule is very powerful, especially if you can if you take the composite or the multiple segment Simpson's 1/3 rule, it really works very well. In this particular problem, it we got for n equal to 4, we got an error which is 10 to the power minus 3% in percent, and it is only in some 11,000 plus meters you get an error of 0.3 meter, which is less than a meter, and this is the strength of this method for evaluating an integral. So, what it does is that once again, just to remind you that you replace the integrand by a polynomial, and then for a problem that is unknown. So, when you have x0, fx0, x1, fx1, x2, fx2 and all that. So, when you have a series of, or rather a set of data points, then you need to have a polynomial, and you could, as I said, that you could have a polynomial going by the Newton's interpolation formula or by the Lagrange's interpolation formula or by any other formula. It is not going to make a difference to the result that we have obtained. That is just quoting the result for the single segment, that the value of the function at the left interval, value of the function at the right interval, and multiplied by the plus the value of the function at the midpoint of these two intervals multiplied by 4, that is, this comes with a weight of 4. All right. So, so far we have discussed with equally spaced points, as if because these x0, x1, x2, x3, they all differ from each other by some step size, uniform step size h. So, let us just write that. So, so far we have considered equally spaced sampling points. Okay. And it could happen that in a particular experiment you do not have these equally spaced sampling points, and then these Newton's interpolation formula cannot be used. But as we have said that the Lagrange's interpolation formula can still be used, which really does not require equally spaced point. But here we will discuss another method to to handle points which are not equally spaced. Let us see, these are called Gaussian integration. we will relax the criterion of equally spaced sampling points. Okay. So, in order to go about doing that, let us give you an example of this particular thing of this trapezoidal rule. But before that, let us say that what is this Gaussian integral. So, this Gaussian integral or this integration formula, which is also called as quadrature formula. So, if you see in literature a quadrature written, it means the same as this the Gaussian integration formula. So, it utilizes the concept of increasing accuracy of the estimation of the integral, of course, by choosing the sampling points wisely. Let me underline this and try to say that what I mean. Okay. So, what is meant by wisely? So, what I want to say is that we do not want to blindly choose the extreme points and the points which are half of that and so on, but in case we can make a distinction of the sampling points in such a manner that it gives me the best estimation of these for the for the integration, then I think our job is done. As an example, let us look at this. So, this is a f of x versus x plot, and when we have a to be like this and b to be like this, then simple trapezoidal rule uses a straight line between f of a to f of b, and the width, that is b minus a, is simply multiplied by the values of the function or this the average of the heights and things like that. Okay. But instead, so these are, we use these sampling points as the points of integration, the lower and upper limits of the integration, and find the values of the function at the extreme points, that is f a and f b. But instead, if we do that, the following, that is we have the same curve, okay, and we simply use the fact that we do not take these points. So, we take, instead of this point, the a point here, we take a point x, and instead of taking a point b here, we take the point x 2. Okay. So, this is my x 2 point, and then what I say is that I will use this trapezoid and calculate the area of the trapezoid. Now, there is a question. The question is that whether this the trapezoid that we get by calculating the area, I mean calculating this integral value of the integral by using x1 and x2 as the sampling points, is any better than that obtained by a and b as the sampling points. That is not clear, and whatever visually, even if it looks that it's better or it's worse, it doesn't have a meaning unless we wisely choose. That's why we have underlined this word wisely. So, if you wisely choose x1 and calculate the value of the function at x1 and wisely choose x2 by calculating the point calculating fx2, then we might get a much better estimate than what we would have gotten with the simple trapezoidal rule by taking the endpoints as the only sampling points. Okay. Now, for that to happen, this wise choice should be accompanied by two things, not by one, that is not only by x1 and x2, but the weights of these points that are associated with x1 and x2. So, what I mean is that when there is a lot of undulations of a function, some region could be actually more important than other regions, and a trapezoidal formula blindly neglects those inflection points and how it is varying and so on. It simply takes 2 points and then does a area estimation of the area of the trapezoid, and which gives the integral of the function. But here we are saying that not only x1 and x2 will be chosen wisely, a corresponding weights W1 and W2 will have to be chosen wisely as well. So, choice of the sampling points and their weights are to be chosen. Let me box this because there is a central idea of this. So, there is no guarantee that by choosing the weights arbitrarily, you would be able to generate better estimation than what is given by the trapezoidal rule, but there is every chance if you properly choose W1 and W2, it will give you a better estimation. Let us see how it can be done by an example. So, let us just write this integral as Ig. So, Ig stands for the Gaussian integral or the quadrature integral, and let us just take a simple example to begin with, where we say that the integral is from -1 to +1. This will have to be, so I equal to 1 to n, and there is a Wi f of xi, okay, where the I goes from 1 to n. So, we have how many unknowns? We have 2n unknowns in this equation. N xi's are unknown because those sampling points, where to pick them is not known to me or known to us, and also n wi, those are also unknown. That is the corresponding weight that had to be assigned to each one of the sampling points is not known. All right. If it is not known, then we have to find out a way to know these things, and we cannot do it for a large n. So, let us do it for n equal to 2. So, specialize to the case okay, n equal to 2. So, we have 4 unknowns in that case because it is 2n, namely x1, x2, w1, w2, the weights associated with that. Now, in addition, let us assume additionally, which means that independent of this above choice, f(x) is approximated by a polynomial of I mean a cubic polynomial, let us say. I mean it could be anything. So, this f of x is a cubic polynomial, which means that it has terms which are 1 x, x square, x cube, and you can actually consider any order, but let us just assume that this is approximated by a cubic polynomial. And if it is a cubic polynomial, then of course, by this formula your W1 plus W2, this is so for the 1, if f of x is equal to 1, then this is equal to a minus 1 to plus 1 dx, okay, which is of course equal to 2. Then you have a W1 x1 plus a W2 x2. Okay. So, this is like minus 1 to plus 1 x dx, which is equal to 0. Then it is a W1 x1 square plus a W2 x2 square, which is minus 1 to plus 1 x square dx, which is equal to 2/3. And finally, W1 x1 cube plus W2 x2 cube, this is equal to a minus 1 to plus 1 x cube dx, which is again equal to 0. Okay. So, if you solve these for x1, x2, w1, w2, we get w1 equal to w2 equal to 1. So, the weights are 1. However, x1 equal to minus 1 over root 3 and x2 equal to plus 1 over root 3. So, you see the sampling points now change from minus 1 to plus minus 1 to plus 1 to minus 1 by root 3 to plus 1 by root 3. So, if you have a function like this, and then your integration is from minus 1 to plus 1, say here, I mean of course, your 0 is now here. Now, 1 by root 3 is like the square root of 3 is 1.73 and so on. So, this is my 1 divided by 1.73 is somewhere here, here and somewhere here. So, let me write it with a different color maybe. So, these are the minus 1 over root 3 and this is minus plus 1 over root 3. Okay. And if you do this, then of course, the formula becomes equal to. So, this I g for the Gaussian, g for the Gaussian, it is f of x dx from minus 1 to plus 1, it is equal to f of 1 by root 3 minus 1 by root 3 plus f of 1 by root 3. So, if you add both of them at these sampling points, then you get this result which is more accurate, and one can test it. I mean, take an example of exponential x dx minus 1 to plus 1. So, this is your, so it is f of x1 plus f of x2. This is of course given for a minus 1 and plus 1. So, we got these sampling points as 1 over root 3 plus and minus, but if you take other values you will get appropriate sampling points for this. So, this is like f of minus 1 over root 3 plus f of plus 1 over root 3, and this is like exponential minus 1 by root 3 and an exponential plus 1 over root 3, and this is equal to some 2.3426961. That's the value, numerical value for that, and exact value you can check by calculating the integral, which is just this and so on. So, this is like e minus 1 over e and so on. and you can find out the error and see that that error is lesser than what you would have gotten using the trapezoidal rule by taking the value of the functions at this point. So, if you take it at f1 and f minus f1 and f minus 1, you would have had a value which is not as close as this compared to the exact value. So, this is one example where we have never said that these x1 and x2, or if you talk about a multiple segment this of this rule, then these x1, x2, x3, x4 or the intermediate points, they do not have to be equally spaced. They can be spaced anywhere with appropriate weights which would appear for the interval. Now, this particular problem, the weights actually became 1. So, one actually had to assign equal weights to both these, but it may not be the case when you take this integral to be having different limits and so on. And maybe you can take a different polynomial that is not a cubic polynomial and maybe fourth order or fifth order polynomial. This would definitely affect the results. We show a very simple example where one of the important constraint is relax, that your sampling points do not have to be equally spaced, and then your the ones that are given, that is the end points that are given or the midpoint of two such intervals, they do not need to be taken. Rather, you can take any point and can use them as the sampling points, provided they have weights such that your estimation of the integral becomes best. So, we want to end this chapter or conclude the integration, numerical integration part, just summarizing that we have done this the method of using the Newton's interpolation polynomial, and have seen distinctly two types of integral to begin with when we are using the Newton-Cotes formula, and where we have talked about trapezoidal rule and Simpson's 1/3 rule majorly, and Simpson's 3/8 rule, which is a slight variant of the 1/3 rule by using one order higher polynomial, and showed that this Simpson's 1/3 rule is an excellent tool for doing the integration. In fact, a large number of these numerical tools for integration, they use the Simpson's 1/3 rule. And then finally, we have shown through an example that how this Gaussian integral can be done by choosing sampling points with appropriate weights by through certain criterion, and the integral can be estimated to give better accuracy for the integral that we are looking for.